In this video, we'll look at some common subspaces associated with a matrix, for example, the row space, the column space, and the null space. So here's the problem. We're given a 3x3 matrix A, and we're told what its RREF looks like. We're also given the RREF of A transpose. First part of the problem is to find a basis for the column space of A. Well, let's look back at the RREF of A, and let's circle the leading ones. So we're looking at the leading one in each of the rows there. We've got two leading ones in this matrix. The idea is to use the leading ones of the RREF as a guide for which columns of A to choose. So if the leading ones are in columns 1 and 2, we're going to use columns 1 and 2 of A for our basis. So here's our basis here. Vector 2, 5, 3, and vector 6, 15, 8 form a basis for the column space of A. Part B, we're going to find a basis for the row space of A. Well, this time we're going to refer back to the RREF, and the rule is to use the non-zero rows of the RREF. So that would be the top two rows here. Those will form our basis. So vector 1, 0, 11, and vector 0, 1, negative 3 form our basis there. C, we'll find a basis for the row space of A consisting of rows of A. Well, the problem we run into here is that the row space does not normally have basis vectors which are chosen from the original matrix. So we can see this in part B. The basis vectors that we came up with were not rows of the original matrix A. However, if we look back at the first part, we see that the basis for the column space does consist of columns of the original matrix. So the trick is to somehow bring the column space into the discussion. We want to also make a connection with the row space here. So maybe we want to say something like the column space of A transpose is equal to the row space of A. So in other words, we can just rephrase the problem now as find a basis for the column space of A transpose. That is something that we know how to do, and we're sure that it is going to consist of columns of A transpose, which are the rows of A. So that's how we're going to solve the problem. Alright, so let's take a look at our matrix A transpose here. We know that it has the following RREF, so we're just going to locate our leading ones. They are in columns 1 and 3, and we're supposed to use the position of these leading ones here as a guide as to which columns to choose. So that tells us we're going to be choosing columns 1 and 3 of A transpose. So why don't we say that a basis for the column space of A transpose will be equal to the vector 2, 6, 4 as well as the vector 3, 8, 9. Okay, and then going back to our original discussion here, that column space of A transpose is equal to the row space of A. We can then say basis for row space of A is equal to the same set, although it might be a little bit more natural just to write these in the form of rows. Really just a notational difference there, because as we said earlier, the columns of A transpose are the rows of A. Alright, so we've answered the question. We have found a basis for the row space of A, and it does consist of the original rows of that matrix. For the last part, we're going to find a basis for the null space of A, and I've just recopied some information from the previous screen. Remember that we've got the RREF of our original matrix. Well, first of all, let's remember the definition of the null space. It's the set of solutions to the system ax equals 0. So if we write this a little bit more formally, it would be the set of vectors x that solve that system. So set of vectors x such that ax equals 0. So what we might do to get started then is just write down our system in augmented matrix form. So just recopy the matrix A here, and beside that we'll write down our 0 vector. Now we're not going to have to do all the steps of Gauss-Jordan elimination here because we can take a little shortcut. If we were to go through the elimination procedure, what we would end up with on the left is the RREF. And any row operations that we do, whether it's swapping rows, dividing rows through by a multiple, etc., those are all going to preserve the right-hand side. So we're guaranteed that the RREF of this augmented matrix is going to look like this. So all we need to do now is solve the system. Let's say that our vector x has components x1, x2, x3, so I'll just write those up at the top here. And we can identify our leading ones. We've got one column without leading ones in it. That would be the last column. So x3 is going to get a parameter here. x3 is equal to t. Our top row tells us that x1 plus 11x3 is equal to 0. So with a little bit of rearranging, x1 is equal to negative 11x3. In other words, x1 is equal to a negative 11t. I think I'll put a box around this information so it's easy to find in a minute. Middle row tells us that x2 minus 3x3 equals 0. In other words, x2 is 3x3, which is equal to 3t. So the types of solutions that we're going to get, x is equal to negative 11t, 3t, and t, or if we write that a little bit more concisely, negative 11, 3, 1 times any real number t. Now what we're looking for is really a basis for this set. So our basis will just consist of that coefficient vector. Negative 11, 3, 1 will be a basis for the null space of A.